Okay, so let's get started. And here's our next talk. Stanislav, back to you.
Hello. Thank you very much. I hope you can hear me. I'm really terrible in using microphones, so I hope it works now. If not, please give me a huge shout, scream, whatever. Thank you very much for coming. My name is Stanislav. I work as a kernel manager in Red Hat, and this talk will be a little bit about very basic introduction to the debug information, which is very boring. And the very exciting part is about how you can use gzip to make your stuff smaller. So I wanted to make sure your expectations are set correctly about the interesting stuff in the talk, and you won't be disappointed by the end. So what the debugging information are, through the history there has been several different standards, but at today the Divoire debugging information is kind of standard on all Unix systems. So it's Divoire because it's the counterpart of ELF, and ELF is the executable linking format. So the Divoire is joke. They have this wonderful logo with a real Divoire in the middle of it. Usually people just care about debuggers. So debuggers complain if they don't have debug information. So just compile with the -g option. It will generate the debug information. That's enough. Then the debugger complains a bit less, and you can use it for actual debugging. Currently, version 4 was released. Version 5 is almost ready, and I guess will be released very soon. What it really is that because it's counterpart to ELF, it's really built on top of ELF. So ELF is an interesting format which allows you to ship your binary data and executable files, and it provides two views on the data in the way how it's stored in the file and in the way how you can actually execute it. So what Varf is doing is that they are introducing a couple of more sections or program segments in your ELF binary, and these sections contain the real debug information. There are about, 8 of them, usually about 5 or 6, but maybe the most important sections are the debug info, which contains the real type of your debugging information, the debug abref, which are the abbreviations, which is the real type schema, but it really goes very closely with the debug info. So I would just say that these two should be considered as together like one thing. It's more of a space optimization. And another interesting section is the debug line, which contains kind of virtual machine, which can be used to identify which type has been defined at which planes in your source code. So then you need to have your actual source code next to it so you can find the proper place where it was defined. It's not used only for debugging, but also for some tracing tools like SystemTap or the things built up of kprots, which is the internal kernel stuff, how you can actually trace the kernel itself on Linux. So this is just a very brief example of using readelf, which is a program which can be used to read your ELF binaries to dump the ELF sections, and you can see that there are a bunch of various debug sections which you need to look at if you care about debugging stuff. So what it really is inside the debug info and debug abref sections is that it's a type graph. There are basic nodes in the graph. They point to each other as they are referenced, and etc. The real graph is formed by a linked list of compilation units. So a compilation unit or a translation unit, or for C programmers, an object file. That's the basic unit which you compile. So the C source code, right? You compile each file separately, and then at the end you just link them all together. And if you have a very nice linker, it will do some optimization. So the debug information follows the same process. There's one compilation unit for each object file, and then a stupid linker just puts them all together in one linked list, and it's done. It's very easy. For each compilation unit, you have a type graph of the DICE, which are the debugging information entries. So this is a real graph which tells you which type is pointing to which type, and where you can very easily follow how all the types are interconnected. It's oriented graph because you can really follow the edges, how they are referencing to each other. Each die also has attributes like the name of the type, or the size of the type, or this kind of stuff, which is really like whatever you would need to know. So writing a linker which can link your debug information is really easy task. This is an example of how a specific die, the debug information entry looks like. So we can see that there is a type of the die is a structure type because it's the beginning of some C structure. It has about 5 attributes. It has a name, size, where it was defined, and it has some sibling in the graph. So how it really looks like is something like this. You have a linked list of compilation units, and each compilation unit has some random graph of types which are somehow connected together. And now you see the obvious problem, right? A lot of types can be actually stored several times in the debug information entry. So I think that just for fun, I'd look at the VM Linux, which is the base of our kernel we ship, and I think that a definition of a task struct, which is the structure which represents one task, is stored there, I think, 250 times. So it's really not very efficient. If you can just merge the same types together, it really becomes smaller. Okay, this is really obvious, so everybody knows that, and people look at it, and even the Divoire standard committee look at it, and it's part of the Divoire 3 standard. So what do you have in a Divoire 3 standard is that you can create a virtual compilation unit, which is called partial unit, and then you can link this partial unit into all other units which actually need this data in the form of imported unit. So it's great. It's like wonderful. We can finally move all the same types into a separated virtual partial unit and then link it in all the compilation units which need them, so we can unify all the identical types. I think it's just my private opinion that the Divoire committee thought that a compiler would do this at a time of linking, so it's kind of link optimization thing. In reality, I think it didn't happen, but what Jakub Jelinek did in about 2012 is he wrote a DWZ tool, which is a Divoire compression tool, which is exactly what it does. So it looks at all your compilation units, it identifies the same types, it moves them to the partial unit, and it links the partial unit from all of them. So you can just very easily run DWZ on your binaries, and they should become smaller. Very trivial example, I have a program which has a debug info of 428 hexadecimal bytes and a bref section of 1D8 hexadecimal bytes. After I run DWZ, it becomes about 1/3 smaller. So it works. If you look at it at the dwarf level, you will see that there is a partial unit which contains my structure type, and it's later linked to all the compilation units which need it. So this is how it looks like after you do the unification. The compilation units which need the data are linked to the dies which are in the partial unit. The partial unit is really virtually copy-pasted into every compilation unit which needs it. So if you use this on something bigger like VM Linux, for example, you will see that the debug info in VM Linux after you compile it is about 140 megabytes. There are 2 megabytes of abref section. After you use the tool, it becomes 41 megabytes, about 1/3 of total size. Wonderful. I know that Fedora is doing it for all the packages it ships. I'm not sure if it's done for the kernel, but anyway, this is the way how you can make it about 1/3 of the original size. It's really I would recommend it very much. Now let's step back and think completely different. What else we could do instead of working in the boundaries given by the Divoire standard? Maybe stupid idea. Let's just strip the debug info sections out of the binary. That's what I'm using EUstrip for this. So the first line, EUstrip, I'm stripping all the debugging information sections out of the VM Linux in a separate file, which has 74 megabytes. Then I gzip it, and it has 30 megabytes, which is really not great because these are random binary data, and gzip is not very good in decreasing the size of random binary data. So good try, not the best. What we could do else? So the DWZ is a tool which works with your debugging information entries, which it needs to be very cautious about what it does. Because when you are debugging, any slight change in something might actually make the debugging much harder. You need to make sure that whatever you look at is absolutely correct, and you can see all the stuff. But there's another completely separate tool, which is its goal is to allow an ABI comparison of the library. So you have two libraries. You wonder how much the functions and types they work with differ. So you can use a tool called libabigail, for example. There are others for the comparison of the binary data. What is interesting is that how it internally works is that it reads all the debug information sections into memory in all these graphs for all the compilation units. But then it merges everything together. And is more aggressive than what DWZ is doing, because for the ABI comparison, you don't care about little tiny differences. As long as the binary representation is the same, you can merge the things together. I will go a little bit deeper into this later, but let's say it's more aggressive. So you get a less number of nodes after this unification is done by libabigail, for example, or any other decent ABI comparison tool. The libabigail can also dump its output in the form of XML file. XML is, I think, really very inefficient in the way how it stores data, but whatever, it works, and it somehow gives us a file which contains the layout of your binary structures. So this is how it all looks like. ABI DW is one of the tools which is built on top of libabigail and is shipped as part of the libabigail. So you can tell it to actually load all the types, all of them which are even unreachable files from the export interface, and just dump it in a file, and in file you will see an XML element which contains what originally was in one of the debug information entries. So there is a they say class, it's a C structure, but because libabigail is written in C++, they don't work with the term structure, they use the term class. So we create a class called foo, which is 64 bits in size, and there are some other attributes of this type. So when I'm saying that it's more aggressive, what does it really mean? This is the most trivial example of what I can show you. Let's say there's one header file which defines one structure, but it declares the inner structure. So for the structural foo2, we have just a declaration. We can't say anything about its size. We don't know what it is. So we have a declaration of foo2 and a definition of structure foo. Then we have one file which defines the internal structure. So we have a full definition of structure foo2, and then we have another file which just doesn't care about the internal type. So it is fine with the mere declaration, and it just works. So if you think about how type graph would look in this case, we have two compilation units. We have the same debug information entries in them for the same type of the same size. Anything what is in there is the same, but they differ just in one thing, and that is that the internal type in one case is just declared. In the other case, it's fully defined. Would you merge it together or not? So on the ABI level, they still can be exactly the same. So libabigail is merging them together, while DWZ isn't, because the types are different. In one case, you don't have any information, while in the other, you have all of them. So it might be different. DWZ doesn't merge them. I'm trying to show it here that at the end, you see two different types in this very example, while libabigail does. It merges them together, so at the end, you will see the foo2 only once in the resulting file. And I'm being too quick. How are you? Anyway. How it really works is that if you use libabigail on VM Linux, for example, it will build a graph, it will all unify it. So at the end of the first line, I'm just dumping the output in a file. This file has 36 megabytes. It's already less than what we have seen with the debug information. The XML text file is smaller than the binary representation, which was designed with the size in mind. And then because it's text, you can very easily run it through gzip. So at the end, we have 2.6 megabytes of data which still contain all the debugging information entries for all the VM Linux file. The VM Linux file has, in my case, I think it was about 28 megabytes or something like it. So we are able to store complete debugging information for VM Linux in about 13% of its original size. So now that's interesting. It's really, this doesn't exist. It's just an idea which, it's good to know. What we could do with this. Currently, if you need debugging information entries, for example, for the live tracing of your kernel, the only way to get them is that you install the debugging information files on your system, which have like 130 megabytes or something like it, so it's pretty huge. And then, anytime you need to actually trace a specific point in your kernel, you need to have some userland program which will look at the debugging information entries. It will find the real position in your kernel, and it will then instrument the specific place in your kernel. So this is how example systemtap works, right? It's a userland compiler which will look at the debugging information files. It will find what types it needs to trace. It will look at the offsets, and then it builds the kernel module, which it pushes in the kernel. And this kernel module has hardwired offsets it needs to look at. This is also like, for example, the eBPF, the extended Berkeley Pocket Filter, has recently been extended that it can actually be used to enable the kprobes in the kernel. But you need the very same information. You also need start in userland, look at the debugging information entries, and build your specific program with the right offsets, and that's how you push it in a kernel. So what I'm thinking about is like, what would happen if we would just build a kernel VM Linux binary, link to it directly this raw data, which is 13% of the size, so our kernel binary will be bigger by 13%. Then when the kernel boots, it could unpack the data. So it will eat 36 megabytes of our kernel memory. It's bad, but for this price, we have all debugging information in the kernel, always correct. So we can then tell the kernel to trace itself. We don't need to care about offsets anymore and layout and arguments and functions because the kernel knows. It will be, at the end, it should be much more stable and really handy. Okay, we have plenty of time. That's pretty much it. It was really open, very open-minded about like, what are you thinking about at night? So this is what kind of I'm thinking for the last 3 years. Do you have some interest? Any questions, comments?
So why would you need to compress ahead of time?
Why would I? The question is how I would compress it ahead of time.
No, why would you need to decompress ahead of time instead of doing it dynamically when you try to access the data?
Right. So the question.
Get random access?
The question is why I would decompress it at the boot time instead of right in time when I need the data. The answer is that this really doesn't work well enough because what you would also like to have is a quick way how to search your debugging information, which Divoire isn't really good at all. So what you really need to do is, for example, I need to see a definition of struct foo. It's one of the 10,000 types I have in my kernel. What you have to do with Divoire is to just walk all the list and find it. This is not very good. I would really love to have, for example, a hash table next to it. So you could look at a hash table, find it, and go to it. But you can't do this if it's all compressed. So that's why what I was thinking about is let's first uncompress the indexes so we have something very quick and very stable for lookup of anything we need.
Yes, but you could do that by some access to some special device or whatever, or raw country or whatever.
Sure. The comment is that we can do this by access to a device, for example, or whatever, at the time when it's really needed. Sure, we can. Right, absolutely.
I would like to know that there is already in bar 5, there is .debug underscore names, which is index for all the elements, all the dice. So you already have their index, and in bar 4 in Fedora there is .gdb underscore index, which is Red Hat extension,
right,
which is now in bar 5 standardized.
Thank you very much. The comment is that with Divoire 4 in Fedora, we are shipping a non-standard extension which already contains the index for all the types, but in var 5 this becomes part of the standard. So with var 5, which is really going to be released very soon, there is a way how to have a fast lookup index for your var data. Thank you.
And I would like to also note that you say that the DWZ does not compress it well enough. In fact, nobody says that, but there is such public secret that DWZ compresses it in a way it stays compatible with current tools. As DWZ could just take all the types and put all the types for the whole project into one big partial unit and import this partial unit in every compilation unit. As due to ODR, one definition rule, at least in C++, any class needs to be the same across the whole project. And therefore there can be one definition, but for example, GDB loading such a big partial unit for each compilation unit would die on it. So, and other tools would also have a problem with such big compilation unit after their extension. So, that could be improved, but there is a problem with current tools.
Right. Thank you. I said that DWZ is trying to be very cautious and very safe, and the comment was that it also, whatever it does strictly in line with the standard, and it's really cautious and really tends to be on the safe side of things. So it doesn't produce a big compilation units, for example. Right? Thanks. Okay, one question there.
Well, it's not a question, but rather a comment. I don't want to downplay your work, but the main, debugging is not a very common operation. And as far as I know, the main requirement is the speed of operation rather than size of extra debugging tool. And I see the remarkable result of your work in that way. Current debugging data stores is so ineffective, but even exhibit XML can beat it rather easily. So this is it. But seriously using XML as a replacement is not a very good idea, because searching through the 70-something megabytes of XML is not a fast operation. Why not using SQLite, for example, exhibit SQLite? Did you try it?
Thank you very much. It actually is a question. Why not use something better than XML, something better for searching, for example, SQLite database or something like? I'm totally with you. This is not my idea. I hate XML. I hate it, but that's what libabigail generates. And for the purpose of libabigail, it works. It works well enough. And I just use it because it's there. It works. It was easy for me. What I wanted to show, it works. But definitely, if I would like to produce something which would be smaller, I wouldn't start with XML. Thank you.
Couldn't you just recreate a Divoire file which is more compressed from the results?
The question is if we could recreate the Divoire file which would be smaller from the results. Whatever we would create at the end based on the XML file would be different from the source because it's already after the unification. So we have already merged the types which are in there. So if we would be able to produce a valid Divoire, I don't know. It's very likely. But it would be very different Divoire from the original Divoire. And as our colleague here said, So we destroy the compilation units. We just merge it all together. So if we would create the Divoire from the final result, it would be just one huge compilation unit. So for example, GDB could have very hard times opening just one huge compilation unit. Right? One question in the back.
A few questions. First of all, it's pretty cool. And the question, did you consider to try to unify people information across different executables, or even L files? In standard library, you probably will have much of the same subtrees, which is also interesting to compress. And second
So there are two questions. The first one, can we build a one common debug information across several separate binary files?